Welcome to today's webinar, Data Exchange between Rhino, Grasshopper and RFEM6. My name is Andreas Hörold. I'm responsible for marketing and public relations in the Dlubal Software company. For instance, the Dlubal website, German and English webinars, etc. I will be the moderator today and I will answer your questions. My colleague Lukas Sühne, he will be the presenter today and he can introduce himself.
Yes, hello also from my side. My name is Lukas. I work for Dlubal for 10 years now and I'm working in the steel design and interfaces department. And as Andreas said, I will present the Rhino Grasshopper link to RFEM6 today.
Okay, thank you for the introduction. Then we can switch off our webcams that the attendees can see the full screen. You can ask questions via the control panel on the right side of your screen. You can enter a question here and I will answer you. If you don't get an answer during the webinar, because there are too many, you will get an email afterwards. The other way is to watch the entire webinar and then email your questions to info@dlubal.com. To the agenda today, Lukas will start with general information, such as registration and so on. Then second point is data exchange between Rhino and RFEM6, and then the same for Grasshopper and RFEM6. Okay, then I hand over the screen to Lukas. Lukas, it's your turn.
Yes, thank you very much. I will switch the PowerPoint slide. Maybe you can tell me if you can see it.
Yes, requirements.
All right. Okay, then as Andreas said, I will start with a couple of general information regarding the interface. And I would like to start with information regarding the installation and the requirements that you need to use for the use of the Grasshopper link. The first information is the installation of the plugin must be done manually. It's a bit different to the past. It's however not complicated. You can install RFEM6, doesn't matter if it's the customer version or the trial version, and after the installation you will find the Dlubal RFEM6 plugin.rhi file in the folder you can see here in the picture. You can simply double click on that file and the plugin will be installed. Both programs are communicating directly with each other. In RFEM6 we're using the web services for that. It is the replacement for the old COM add-on for RFEM5 or the COM technology that we used in the past. At the moment, the situation is like that the users require a web service license to use that interface. We plan to remove this limitation, or we plan to develop it in a way that every direct interface that is made by us, for example to Grasshopper and Rhino, or in future also Revit and Tekla, should not require a web service license. Again, the actual situation is different. So if you would like to test it, or if you would like to use it for a while, send us an email and we can arrange this license for you. The last information, so when you installed RFEM6, you installed the plugin and you have a web service license in your pool, then please go into the RFEM6 program options. On the bottom of the options list you will find the setting for the activation of the web services. So make sure this check is active and then you are ready to use the plugin. Now a rough overview about the plugin itself. The Rhino Grasshopper plugin is actually two plugins. We have a Rhino RFEM link and a Grasshopper RFEM link. The Rhino RFEM link is similar to what we had in the past, and by that I mean of course RFEM5. You have an import and an export options to transfer simple objects, lines and surfaces. The basic geometry, no additional information related to them. No materials also. We improved it a little bit, but it's more related to the handling itself. You will see that later on when I present it live. More work went into the RFEM Grasshopper link. Here let's say we also have an export mainly, and we are working on the import. And regarding the export, we support model data and supports. So we increase the amount of features in our model data components. Yeah, you have more control over the structural analysis system, basically. Additionally, and this was also a big wish from basically all customers or all users that were dealing with this topic, we implemented load cases and load combinations into Grasshopper and also the loads. Not all loads and not every feature can be controlled via Grasshopper, so it's not the full list of features of RFEM 6, but we tried to pick the most common ones here. If you're missing something, let us know. It's quite simple for us to implement additional features, in general at least. And for those users that are still not sure what I'm talking about because they're just interested in this webinar, what this is about, I would like to explain again quickly the workflow that you can realize with Grasshopper and Rhino and the add-on that we have. In general, you could say the Grasshopper or Rhino and Grasshopper in combination with the Dlubal plugin is an alternative method for the model generation. Yeah, instead of creating your structure manually in RFEM 6, you can use Rhino and Grasshopper to generate the basics for a structural analysis model, the lines and the surfaces based on algorithms. Yeah, you don't draw them there. It's more like a programming logic, and in those algorithms, you can assign parameters to a structure. So at the end, you have a parametric algorithm to create these basic geometric information. And then you can use the Dlubal components to assign additional informations to those elements. So regarding the lines, you assign the cross-section, the materials, maybe some eccentricities, so that at the end you get the member in RFEM 6, or for surfaces, the thickness, again, material, and so on. So at the end of this workflow, you get a structural analysis model in RFEM 6, and that you can, of course, analyze and design there. And at the end of the story is, of course, also the visualization and documentation of the results, again, in RFEM 6. What we are working on, what is not ready so far, is the import back into Grasshopper. So the plan is to read the results from the analysis in RFEM 6 back into Grasshopper. And with those results, you could run additional optimization routines, or you can even use them to visualize the data. So this is a rough overview about the plugin, and now I would say we take a look at it. We will start with the simple plugin between Rhino and RFEM. Therefore, I will open Rhino on the left-hand side and RFEM 6 on the right-hand side. So, regarding this simple plugin between Rhino and RFEM, you can see here on the left I have a small Rhino structure. It consists of surfaces and lines, basically. Also the beams down here are actually surfaces. If I click on that, you can see in the details it's a NURB surface. So the structure itself is also grouped into layers. There is a layer for my roof. Then I have a layer for the diagonals and for the beams inside. All right, so this is what the structure is all about. And let's say you would like to export now something into RFEM 6, then it's quite easy to do. After the installation of the plugin, you get these two icons here for the export and the import. And you can use it, of course, to export the structure to RFEM 6 by simply clicking on it. And this export dialog gives you following options. You can overwrite the RFEM structure. This is the option we had in the past. Yeah, everything will be deleted before we export, and then the new data will be exported to RFEM6. The alternative, and this was also wished by a lot of customers, is an append option. So yeah, these are the two options that you have. Additionally, you can flip the Z-axis coordinates during the export. You can see it here, the global Z-axis goes up. In RFEM it goes down. I would like to avoid that my structure is upside down after the export, so I check on this option. You have in shift, so you can move the structure during the export, and I think the values are related to the units that you define in Rhino. And the last two options that we can see here on the right-hand side is we can select the layers that we want to export. So basically, the content of the layers will be exported. Yeah. So this is one way to control the amount of data that I export to RFEM6. The other two options are selections. So alternatively to the layer selection in the dialog, I can also simply select the objects that I want to export, or use visibilities in Grasshopper. You can also hide objects, and then only the visible objects will be exported. There is no additional check you have to set to do it like this. Yeah. Whenever you hide something, it will not be exported, or whenever you select something, only this will be exported. So let's do it quickly. I can export, for example, let's say only the content of the roof and the diagonal layers. And the last option that we can use here is use layer identification. That refers also to a wish that we got in the past. There was a wish to create automatically visibility in RFEM when we are exporting whole layers. Yeah, so let's say automatically in visibility for the roof or for the diagonals. We didn't manage it completely, but with this option it's quite easy to do afterwards. This option basically writes the name of the layers as a comment into the surfaces, and based on these comments you can create visibilities in RFEM6. I will show it in a second. So first of all, let me export a couple of surfaces, so the roof and the diagonals, and yeah, you get this window during the export. This shows you that the communication is running, and now you should keep an eye on RFEM6. Check when the structure shows up, because this is at this point the export is finished, and this is important to know. You can see it in a second. So now the export is finished. You basically have to manually close this window. You don't have to wait until it's closing automatically. This could take some time. Just abort and click yes. We're trying to optimize this behavior, but it's a bit tricky. So the export is done. Yeah, we have the roof layer and the diagonal layer, so the same content as in Rhino. And yeah, you could use it now to model the structure in RFEM6, which, however, I don't want to show today. I want to show the last option that I explained in the export dialog, the layer identification. So if I go into the surface table, you can see here in the comment, in the last column, you can see the layer names for the surfaces. Yeah, some of them are related to the roof, some regarding to the diagonal layer. Now we can create manually user-defined visibility, or a so-called object selection in RFEM6. So let's say I want to have two object selections for the roof layer and for the diagonal layer. You simply say, okay, maybe we can assign a name first, roof, and then you select all surfaces with the comment equaling to roof. And we can create a copy. We name it diagonals. And then we change here the comment to diagonals. And now we have two object selections, so basically two visibilities, and they contain the surfaces from those layers basically. Yeah. So this is the way you could create visibilities based on these comments. Yeah, so far regarding the export, there's nothing else I could show here. Therefore, I will switch now to the import, and for the import I'm using a different structure. I have here the RFEM6 file, and as side information, I got this file from our website. So if you go to our website, you can go to the download tab, structure analysis model to download. And then I used here filter tensile membrane structures, but the library is much bigger than the 118 items you can see here. You can download these files and have a closer look at them, in case it's somehow interesting for you. All right, so this structure I want to import into Rhino. It's quite easy to do. You have the import button here. The options are similar. You have the flip z-axis option, the offset, and let's say a little bit different setting here is you can define the layer that you want to import those information into. If you have multiple layers here in Rhino, you can decide should those information, these geometries, be moved into the roof layer, the diagonal layer, or whatsoever. The import is always an append mode, so we will never overwrite anything here. It's always an append mode. So I will import them into the roof layer. Again, this window pops up whenever I see something here. I know the import is finished, and I abort this window. So that's the structure from RFEM6, with the surfaces and so on. So far regarding the Rhino RFEM link, there's nothing else to say or to show. And I think we can switch to the Grasshopper RFEM link because this is the more interesting one, I would say. So let's open Grasshopper and let me create a new file in RFEM6. Name doesn't matter. Okay. So at the beginning I will maximize Grasshopper, and then I will also have this side by side to RFEM6 and to Rhino. When you install the plugin, you will get this menu, the Dlubal menu, and this menu contains the RFEM6 components. We group them into 3 packages. We have the model data group for nodes, lines, members, of course, then surfaces and solids, and also types that you need to define them. So for example, for the surface, you always need a thickness type, or for members, you most likely need a cross-section or a material. And then we have also additional components like the eccentricity, member hinges, line hinges, openings. The supports, of course, are also important. And in my case, I'm using today an internal version of the plugin. I already have new types, the solid gas, and regarding the loads, also the solid load. We are continuously developing this interface. Then we have the second group, the load groups, loads group. Here we have load cases, of course, load combinations, and also the loads at the end, nodal load, line load, member loads, surface loads, free polygon loads, and upcoming the solid load. And the last group here contains the export component and also additional components regarding the import. So the import from RFEM into Grasshopper, and then some filter and data components, which I explained briefly at the end of today's webinar. Let's have a look at one of the components, for example, here the member component, and it has some nice features. First of all, you have this more button in many of those components, and this button allows you to minimize or shrink the component and use just the necessary inputs. And in case you have more optional inputs, more optional inputs can be found in the more area down here. We also have an option to assemble elements. So by default, this component is set to assemble. So with the different inputs, we can create a member. And we have here also a button that allows us to switch it back. So in case we get an RFEM member component, we can also extract the information again out of this component. At this moment, I would like to say thanks to Bollinger and Kroman and Diego Apelanes. They helped us with the development of this plugin, and they also allowed us to use this nice GUI widget. Yeah, this is not developed by us. This widget, it comes from, yeah, let's say Bollinger and Kroman and some people working there. And yeah, I would like to say thank you. And in case you are still using RFEM 5 and not RFEM 6, then, and you are also looking for a good solution how you can transfer data, make sure you check out the parametric FEM toolbox, which is, as I said, developed by Diego Apelanes, who's working for Bollinger and Kroman. That is a really nice tool, and yeah, allows you to import and export data between RFEM and Grasshopper. Okay, so back to the RFEM 6 plugin. I would like to use some of those components today so that you get a feeling for the logic, and therefore I'm using a predefined example, and this is it. Basically, there is the group for the Grasshopper geometry, so my algorithm that creates the structure that I will show in a second, and then I have different groups for the model data, for the load case creation and load combination, for the loads, and also the final export. And I don't have the time to do everything here today, so I will always create the first step for each group, yeah, the first step for the model data, first steps to create load cases and combinations and also loads, and then we will look at what I've done here in this bigger example. Regarding the structure, I have here, as I said, my Grasshopper geometry, my algorithm, and with this algorithm I want to create, let's say, a simple stadium. Yeah, it's like football stadium, whatever, with some beams, of course, a slab on the bottom, and yeah, that's the geometry I'm creating with this algorithm. And while creating this algorithm, I assigned a couple of parameters. So, and with these parameters, I can modify my structure. For example, I can modify the amount of frames that I maybe need to design it properly afterwards. The length of the stand can be modified, the height of the structure, the column overlap, beam overlap. So various dimensions have been parameterized here by me. Also the bracing below my main beams for the stand. So this is what I have here, and as a result of this Grasshopper geometry, you get at the ends, of course, lines, lines for the bracings, then lines for these main stand beams, lines for the beams on the roof, for the columns, and so on. And this is the base for these elements are the base for my RFEM 6 components. I need to assign now the cross-section, the material, and so on to these elements, and then I can export them to RFEM 6. This is what I will do now. So this is where I will start. So basically I will drag it down here, and let's say I would like to start with the modeling in Grasshopper for RFEM 6. How would I start? Well, for every element in RFEM 6 you need a material. It doesn't matter if it's a beam, a solid, or a surface. The material is one of the first things you have to define. So this is why I'm using here the material component. I drag it into my workspace and I will define it. On the left you will find the input values, and on the right hand side of this component it's the result, it's the material at the end. And this is what I will do here. I have 3 inputs that I can fill. Not every input needs to be filled. And the material number is the first information I have to define. Well, it's a simple number. The ID in RFEM 6 afterwards, is it material number 1 or 2 or 3? You can assign it if you want, what I will do here, and then this input is ready. The next input is the material name. This is a text input, so you could enter a text that defines the material, for example, steel steel 235. Yeah. But in general, the name of the material is a bit more complicated. Yeah. Usually a code is also mentioned, or the standard is also mentioned in the material name, and this gets a bit tricky if you have to define it every time again. Yeah, EN 1993 and so on. That's maybe not the best solution. So we got the wish from the customers that to implement a database into this component, and we thought about it, and actually we decided a bit against it, because we are like an international company. We have customers in America and in Europe and in Africa and so on, and the materials are different for every country, and we didn't want to implement the whole library into it. That's why we thought, well, at the end, the best is probably if every customer creates his own library. It's not much work. Usually you are dealing with the same 10, 15 materials, I guess. Yeah. So just create once like a little library, a little list of materials in such a panel component, and just reuse it in every project. And this is what I did here. I have here a material list, yeah, index 0 to 9, some steels, some concretes, and some aluminum materials. And now I can use a list item component in Grasshopper to select one of these elements. So for example, so I connect this list to my list item component, then I can define in the second input my index, which is a simple number at the end of the day. So for example, number 0, and then the result of this component is one item of this list, so one material. Yeah, I can also show it again. If I connect the result into a new panel, you can see, okay, if I choose here index 0, I get my steel S235. Index 4 is a concrete. Yeah. So this is the workflow that I would suggest to customers, potential customers, or people that are interested in using this plugin. And then you can connect the output here into the material name. The comment is an optional input. You don't have to fill it. Yeah. So this is how I can create a material in Grasshopper. Let's say I need 2 materials. I can use copy paste, just modify the slider here. Let's say I want also a concrete C3037, and I also have to modify, of course, the number here for my material. You should not assign the same index multiple times to objects. Yeah, this can cause errors in RFEM 6, of course. All right, so now I created 2 materials. I can continue. Let's say I would like to model some beams. Yeah, for the main beam here in my roof, for example, I need a cross section, of course. Yeah, so this is the base for my member. I need a cross section. So again, I drag and drop this component down into my user interface here, and again I have to fill it with information. I can copy some stuff from above, for example the section number. Yeah, I assign it again. Then the section name, same story. You could manually enter again the name, yeah, for each time you model something. Alternatively, you create a little bit of a small library for the common sections, and then use the same logic, yeah, list item, number slider to select the proper cross section. In my case, I need an IPE 400, so the index number 8, and I connect it to the section name. Now, for a section in RFEM 6 also always, or a material is always assigned to the section in RFEM 6. This is the logic, so that's why the material input is here again. And now you have 2 options to assign a material. You can do it by entering a number, yeah, the index number. Basically, we require here the index number of the material. So you can enter 1 or 2 in my example. Alternatively, if you assigned the ID before, yeah, if you have a material component here and you assigned the ID, then you can also link the material directly to the material number input. So in that moment, we will simply read the number of the material here and put it through into this component. Yeah, what else do we have? Section rotation angle is not required component, also not interesting for us today. All right, we have the material, we have the cross section. Now we can create a member. So that's the next component that I would like to create, a member. And here we have again various inputs. The first one is the Grasshopper line. So this is one option how you can create a member. You can base it on a Grasshopper line. And this is what we will do. And therefore, let's have a quick look at the project. I would like to create beams for these main beams here for my stadium. And this comes from 2 curve components. Yeah, I could have collected it in 1, but now it's 2, doesn't matter. So from those 2 curve components, I would like, based on those lines, I would like to create a member. So I just drag and drop, or I connect these with the Grasshopper input here. Let's have a look. These are 32 lines. And now the next input would be the member number. Well, you don't have to assign an index number to members. It's optional, as you can see here, optional index number. I would like to do it anyway because it will help me afterwards, and I will explain it afterwards as well. The question is, how can you assign now these numbers? Well, one way would be again to create a list. Yeah, a list with numbers and so on. The issue, however, is that this list must be, you need one ID for each line, basically, yeah, because from each line we create one member, so you need 32 IDs. And creating them manually is, in my opinion, no option, not in this case. And it's also no option because this whole structure is parametric. Yeah, whenever I increase the amount of frames, I will have more lines, more beams, and I would have to rework my index list. So I'm looking for an alternative solution. And this could be, for example, a series component in Grasshopper. Yeah, it creates a list, and this list should start with the number 1 index, or with the number 1. Yeah, the step should be always 1. So next number is 2, and then 3, and so on. And now we need to count the amount of IDs or copies, whatever you call them. And this information I get from this list. Yeah, I have here two curve components, and if I connect them into one list, we see there are 31, or actually 32 lines, because it always starts with index number 0. So 32 lines. So if I grab the last index number from that list, then add 1 to it to get, let's say, 32 IDs, then this is something I can use as an index or for the count in my series component. So what I will do is following. I create a last index component. Then the list here is again the list that I just showed. Yeah, it shows these 32 lines. The last index is the number 31. As I said, we add 1 to it. Yeah, 31 plus 1 is 32, and this is the count of my series list here. So I get here now a list of 32 IDs, and this is my input for the member number. Looks difficult, but it's actually not that difficult. And the good thing with this is whenever you change something, it's still parametric. Now I have 20 copies of this frame. So I have here, here, 42 lines, and this list gives me now also 42 IDs. So it's quite good. Good solution, I would say, for this case. All right, what else can we define? Section distribution, is it a uniform member or is it a tapered member? Yeah, you can assign this setting via a value list. You connect the value list to this input, and then you can choose the option, is it linear or is it uniform? There are also other options like tapered at both sides and so on. Not everything is supported here at the moment, we support only uniform and linear. These two options gives you, let's say, the most common possibilities to create a uniform member, of course, and also a tapered member. In my case, I'm using a uniform section distribution. The section start, I think this is clear. We need to define here the cross section. Again, we have two options. We are expecting here the index number of the section. So not the name, but the number of the section. And again, we have two options. We can assign the number manually. So I could say index section number 1. Or alternatively, if I define the ID in that component, I can again connect it directly to the member component. Only if I assign the index number here. Okay, section end. This is useful if you have a linear section distribution, and then maybe a member type is also interesting to know. Again, you can control it via a value list. This should be also mentioned in the comments of this input. Value list, so you know how you can control this input, and then you can define here, is it a beam, is it a tension member, a truss, whatsoever. Okay, with the click on more, you have more options, as I explained. Something worth noticing is probably the rotation type. This was also requested in the past. In the past, we were only able to change the rotation of a member based on a rotation angle. Now we can also relate it to a specific node, for example. I'm using that in my bigger example on top of my file here. I will explain it afterwards. Alternatively, you can assign here hinges and eccentricities. Okay, so far regarding the member component, I think this is also clear regarding the definition. Now, the last few components regarding the model data that I would like to show are surfaces. This is maybe also interesting. It's also based on a Grasshopper surface, so you can connect this surface that I created here, the Grasshopper surface, into this input. You have to assign an index number again, for example, number 1, and a thickness number. Well, we don't define now the material and the thickness directly. We have to assign a thickness number to this component, and this all comes from RFEM6 itself. It's not the logic that we, sort of when we were developing this plugin. It's based on the RFEM6 logic. We have here thicknesses, and if you create a thickness, you assign the material and the thickness to it, and then this thickness will be assigned to surfaces. So here you would have to assign the thickness to the surface, and the same logic we have to use in Grasshopper. So before I can actually create a surface, I have to create a thickness first. I can assign a number to it. Then the material number, again, I can connect it directly. So for example, material number 2, which was the concrete. And the thickness itself, it's again a simple value in meter. So I don't know, maybe 0.4 meter is the thickness. And then we can connect it and it's done. And this thickness, as I said, can be connected to the surface itself. We have more options in surfaces. We can modify the stiffness type, the geometry type, and we have also an option for boundary lines. So you can define surfaces in two ways. You can define it based on a Grasshopper surface or based on boundary lines, and then define the geometry type for that surface. So Grasshopper surface is one option, or alternatively the combination as boundary lines and geometry type. Okay, last option is one of the supports. We have here nodal support, we have line support, and surface support. So basically most of the options that you will need to support your structure. And we also implemented way more features here, as you can see in the More tab for nodal supports, not just the translational spring and rotational restraint, not just the degrees of freedom, but now you can also rotate the nodal supports properly via different settings. By the angle, of course, but also by, you can also direct support to a node or to a plane and so on. Okay, regarding the surface support, this is the one that I'm using today. Same logic, you assign an ID, then you assign the surface number into the support. So there were different ways how we could have implemented this. Should we connect the surface to the support or support to the surface? We decided for this. So the surface, in case you assigned an ID to it, in case you assigned an ID to it, you can connect the surface into the surface support. So this surface will be supported by this type. And then you can define the springs. Again, you have the information in the comments here, how to define it free, how to define it rigid, and then also the spring, in case you define a spring in Newton per cubic meter. So I want to have a rigid support in this case, so I define here INF for infinity, or infinite, yeah, whatever. Okay, and this is how I can define my surface support. So far regarding the model data, so like this is how you could start for the structure. As I said, I did it here for the complete structure, for complete Rhino structure or Grasshopper structure, and maybe let me quickly show what I did. I created also two materials, then multiple sections, yeah, for multiple elements. The thickness for my surface, the surface at the bottom so far, the same as I did it just now. And then I have multiple member components, and in these member components I sometimes define the different member type or a different cross section, of course. For my columns I used this specific or this new rotation type, for these columns of my stadium. I have an I section assigned to them, and if I rotate or if I place my columns on these bends, then the rotation should follow basically. And this is why I used here the rotation via help node and the exact set plane, and then I linked my nodes, which I modeled also here in my algorithm. I linked the rotation to these nodes, so every beam will be located or rotated properly. So this is all I have done here in the model data tab, and we can continue with the load combination or load case creation. So let's jump to the next topic, as I said, regarding load cases. Of course, we need to define the load cases first before we can define the loads. So let's quickly start with this. I can drag and drop down my load case component. Logic is the same. I can define here the load case number, then the name of the load case, which is not really important, but okay. Let's say dead loads, make it short. Dead load is the name of this load case. Static analysis setting, well, this is again a component I have to define before in Grasshopper. Also again related to the logic in RFEM 6. So when I create a load case, I need to define, or I need to assign a static analysis setting to it. And these are types that I can create. Same logic in Grasshopper. So before I can create the load case itself, I have to create a static analysis setting. So this is the component for it. Again, we can create a number. Then the analysis type can be defined via a value list. So the value list is a really common component that you can use here. Is it linear, second order, or large deformation? And the last option that we can define here is the exceptional handling. You may know it if you defined or if you design structures with a lot of tension members. They tend to fail under vertical load situations. They all fail at the same time. Then you get instabilities, and so you can activate this exceptional handling here via a Boolean toggle. This is how you could control this option, and then activate it or deactivate it. So this is my static analysis setting. I can connect it again into my load case. So this load case will be analyzed according to a linear method. And one of the last options I can define here is the action category. Action category is of course linked to the code that you are using. What do I mean by that? So if you are planning to design a structure based on the Eurocode, yeah, you would define this standard in the model or in the base data of RFEM6. Yeah, in the base data of RFEM6, you define, okay, the load cases should be classified according to EN 1990 or maybe American standard or whatsoever, and this should be the same in Grasshopper. So for the action category, we have again a component. And in that component, you can define the standard, and it should be, as I said, the same as in RFEM6. And depending on the standard that you chose here, or that I chose here in this case, you have a different list for action categories and design situations. So you can select here now, is it a permanent or imposed load or wind load and so on. And the information you define here can be linked to the action category input of the load case. So here you can see action category is this information, design situation type this one, and you can simply link it to the load case. This is the logic. Under more you find settings regarding the self-weight. This can be controlled via a Boolean toggle. Did I mention it here? Yeah, it's also mentioned in the comments. Yeah. So these comments should help to work with the components. And by default, the factor in Z should be 1. Anyway, otherwise you can also modify these factors. So this is my load case number 1. Let's create one more via copy paste. I will have to modify the numbers again. Load case number 2. This time live load, for example. Okay. Live load, of course, needs to be assigned also via this component. Now it's not a permanent or imposed load, not live load. Well, it doesn't matter. Let's pick any other action category here, imposed loads. Okay, and the self-weight is of course not active in that load case. So second load case has been created. And now the logical step would be to create a load combination. And this is also what I would like to show. For the load combination, we have again a new component. And in that component, we have to define the index number, maybe a name, the static analysis setting, and the design situation. And the design situation is again something that we need to define in advance. Again, I will quickly show it in RFEM6. If you create a new load combination, you have to say according to which design situation should it be calculated. Is it linked to the ultimate limit state or the serviceability limit state design situations? So before we create the load combination, we have to create a design situation. That's the logic. And because of that, I have also a design situation component here. And let's quickly fill this or define it. It gets a number. The name is actually not really important. Anyway, we can fill it. The name, the type is then again, can then be defined via this component that I showed before. Yeah, here the design situation type. And we would have a design situation according to ultimate limit state 6.10. And then we can connect this output with this input and the component is correctly defined. Now we can start with the load combination. Again, well, we could define an index number, but it's not really required for load combination. We don't use this combination again somewhere else, so index number is not important at this moment. The name can be defined here. The static analysis setting, let me use the same again that I used for load cases. I don't mind right now. Of course, we could create another static analysis setting according to second order and use it there. So design situation needs to be defined. And now the important part is this items input. Because for a load combination, we need to define which load cases should be used inside and also which factors. Yeah. And therefore we have here this item input, and this item input requests for a load combination items component. So there's another component that we have to use. Should be this one. Yeah. So the output of this component needs to be connected to this items input. And in here we have now two inputs, the load case number and the factor. And to define a load combination, we have to follow following rules. We have to create, for example, a small list. And in that list, I can say, okay, I want to combine load case 1 and load case 2. Yeah, let's say I would like to have a load combination 1.35 multiplied, the factor 1.35 for the dead loads plus 1.5 for the live loads or imposed loads. Then I need load case number 1 and load case number 2. And this is basically the list for the load case number. And I can copy the list. And in that list, I define the values, 1.35, 1.5. And this is the factor. These lists will be combined. Yeah, this component will create a load combination for it. And then finally here, we will get the load combination. Okay, so far regarding load cases and combinations, I would like to show it again in the bigger example that I have here. I created 2 static analysis settings, then a couple of load cases, 3. It's the German names here still. Anyway, it's dead loads, imposed loads and wind loads. And then I created the 2 design situations for the ultimate limit state and the serviceability limit for the SLS design situation. And at the end, I created my load combinations. And I created 6 load combinations, 3 for the ultimate limit state, 3 for the serviceability limit state. And I've done it the following way. Again, I used my load combination items component, to combine load cases and factors. And well, at the end, it's just the combination of lists. One list always is for one load combination, basically. So this list is for load combination 1, just the self-weight multiplied by 1.35. Second load combination, load case 1 and load case 2, combined by these factors, and then load combination 3, load case 1, 2, 3, combined with these 3 factors. And then I did the same for the serviceability limit state with different combination factors, of course, and this all result in 6 load combinations. Okay, so far regarding load combination, I hope and think this is also clear. And now let's focus on the loads because we are slowly running out of time. So the last step, or one of the last steps, would be to create a load itself. And therefore, again, we have nodal loads, we have line loads, member loads, surface loads, solids loads will show up in a couple of days or maybe a few weeks, and free polygonal loads. Again, whenever you need something, let us know, we can implement it. In my case here, I need the member load, or I would like to show the member load. And the input, and I hope you understand the logic a bit. We can define, we can/have to define the index number of the load. In this case, it's optional. Again, I don't have to define it. What I have to define is the load case in which this load is assigned to. Here I can again link the load case itself, for example, the live load case into this input. And I also have to define the member numbers, which is important, the member numbers to this load. So I have to define here on which members this load should be placed. And this is why it's good to assign numbers to members, because then you can, let's say we want to place this load on all beams, you can connect the member component to this member number input. But again, it's only possible if you assigned the numbers here beforehand. If you don't do it, then I will explain how you can do it alternatively in my main example. All right. And the rest of the input is often controlled via this value list. Oh, not the value tracker, value list. Yeah, the load type can be controlled via a value list. So is it a force? Is it a moment? Is it a temperature? Again, we do not support all these types for now. We support force, moment, temperature, and maybe even some internal pressure. If you need something, again, let us know. We didn't want to enable everything at the beginning because I think mass is probably not often used and so on. And we didn't want to do everything at the beginning because it will increase the size of this component drastically. And yeah, we want to make a compact component at the beginning. Okay, so load type should be force, load distribution, again, value list. Could be concentrated, could be trapezoidal, in my case uniform. Yeah, we stick to the simple definition here. The coordinate system, it's related to the global coordinate system. The load direction, again, a value list. For example, in global Z direction. And then we can define the load magnitude. And this needs to be defined in Newton per meter or Newton millimeter or Newton meter per meter if in case you define a moment, or bar if you are dealing with internal pressure. Okay, let's say 5,000 Newton per meter, which is 5 kilonewton per meter. This is my magnitude. The other inputs are related to other load distributions, for example, trapezoidal, then you need distance and maybe additional load magnitudes. Okay. Yeah, this is how you can define the member load, and now we have to export all those components that we've created, and therefore we have here this export component. We have two major inputs. We have a run input, which allows us to control the export. So it could be controlled via a button. That means whenever you press the button, the export will take place. You can connect this button to the run import. Alternatively, the Boolean toggle command. In case you want to leave the connection open, you set it to true, connect it, and then you have like a live update. Whenever you change something here, it will trigger a new export or automatically a new export. Okay. The second thing that we have to define is the input. The input is of course now a bit of work because we have to export. We have to connect anything that we want to export into this input, and this starts of course with the materials. Then the section needs to be exported, the member, and now this will take a little bit of time, not that much, but let me quickly do it. The thickness and surfaces needs to be exported. So it's not enough to export just the surface, you also need to export the thickness type. So make sure you don't forget something. Then regarding the load cases and combinations, of course, it all starts with the static analysis setting, then the load cases, and the design situation, ultimate limit state, and finally, the load combination. And at last, of course, the member load itself. Make sure you hold the shift button pressed, otherwise you have to start all over. Okay. What additional options do we have here? Well, we have an option to control the units. Again, via a value list. This is the same as we had it in RFEM 5, I think. You can control are the units that you are using in your Grasshopper file, is it meters or millimeters or whatever? These values are related to meter. Okay. Then you have the flip z-axis setting, which I'm also going to use here via a Boolean toggle, to not have the structure upside down in RFEM 6. Tolerances are only interesting if you have nodes being very close to each other. It could happen that during the export nodes will be merged. This is related to, let's say, to settings in Grasshopper itself. Yeah, here you have a specific tolerance setting, and you can modify the tolerances via this input. Yeah. Then what's also interesting, only get RFEM data, I will explain later. And this is maybe also interesting. We have, let me copy this. We have an option which allows us to override the RFEM file during each export. So if override is set to true, then every export is basically overwriting the existing data. If we set it to false, then we will add the new data into the existing RFEM file. And basically, we also have a modify option, because if you assign an ID to every component and you modify and you, yeah, let's say you in RFEM 6 you already have a structure with let's say 100 members, and you create here a member. You say, okay, I want to modify member number 35. Yeah, you define member number 35 should be modified, and maybe you need to modify the member type, for example. Yeah, it should not be beam, but I don't know, trust member, and you put this into the export, then only the member with the ID 35 will be modified. Yeah, the other components won't be touched. So it's also some kind of a modify option. Okay, in my case, I want to overwrite the existing file, and yeah, now I can start the export. Let's see if it's working. Let's hope I don't made a mistake today here. I'm pressing the button, the export starts, and in a few seconds I should see what I just did, and this is exactly what I expected. Let's maximize it for a second. I exported the surface with my surface support. I exported the beams. Yeah, it was where these, it was, I don't know, was it 32 or so? I think I maybe even modified, no, lines members. Yeah, these 32 beams, yeah, 32 lines that I used for the beams. I defined some load cases also with the loads on those beams, and also a load combination should have been created. Yeah, design situation, ultimate limit state, and the load combination 1.35 and 1.5. So this is what I just created, and now I would like to show let's say the final workflow by showing what I've done here. And there's one more thing that I want to mention. I made a little bit different approach in my case, because the members that I defined here, I did not assign index numbers to them. So an index number is usually an optional topic. Yeah, you don't have to define the index numbers. You can leave them empty, and what will happen is when you connect them all to the export component, yeah, you connect this member component and this component to the input here, then internally we will build up a list and export these elements accordingly, and during the export, RFEM will assign IDs to them. Now, why is it maybe not so good to leave it empty here? Well, you have an issue if you are planning to assign loads to these objects, because in every load object you have to define on which member number should this load be applied to which member number. Yeah? And if your members have no IDs, then you cannot link the member to this input here as I did it before. And because of that, we have this read from cage, or because of that I made this small workaround. And here I'm using a regular export component. This is my export component with this specific option, only get RFEM data. So this option runs a theoretical export to RFEM. Yeah. So if I set this to true, it will do a theoretical export to RFEM. It will assign all these IDs, but it will not create geometry in RFEM 6. And I can use this package of data and extract the information again via this data component and split it up again. So this is called GUI object. This GUI object will be split up into member GUI objects and line GUI objects. And I can then use the extract functionality that I showed at the beginning, assemble or extract, to read the IDs out of these components. So from members I can get the ID, the index number. And of course the question is from which member or how can you filter the members? Well, there is a filter component, and I was filtering here based on comments, and because of that I assigned comments to all my members. I think those are the ones that I'm using. I have here a member component for my stage beams, and I assigned here the comment in German, sorry, Trägertribüne, and I can filter now this whole package of members I can filter out the members with the comment Trägertribüne. So from these, and I can show it now, from these, let me see, 252 members that I theoretically would export, I filter according to Trägertribüne, to this comment, and I get here 16 members. And from those 16 members, I extract the ID, and this ID I assign to this member load component. That's the alternative way how you could, let's say, create loads. You either define the index number beforehand and then just connect the members to the loads, or you make this workaround via the theoretical export. Okay. When this is done, you can run the final export, so another export component where again everything is connected into the input, and then the final export will take place, and it will happen in a couple of seconds. I set them all back to false, and here you can see the final result. I will quickly maximize it. I have my stadium here with the beams. I think some of them are truss members, some of them are tension members. So everything correctly defined. I have also my load cases and combinations here, dead load, live load, wind load, and my 6 combinations, and also some loads that I defined on these members. Just as an example. And this is now a structure you could design or analyze, at least in RFEM 6. You can analyze it directly. It's a functional analytical model, and run the design afterwards, I guess. All right. So far regarding this Grasshopper RFEM plugin, again, we plan to one of the next steps to read those values back into Grasshopper to run some additional optimization routines, but this needs a bit more work on our end. Now, before I end the webinar, I will have a quick look at some questions, but as far as I can see, most of them are answered, or all of them. So maybe we can even end the presentation here. Or at least I hand it back to you, Andreas.
Okay, thank you for this presentation, Lukas. Maybe you can take a look at the questions. Maybe you will answer answer again one question. I would like to show you on our website. I take over the screen, just a moment. So, on our website, dlubal.com, you will find under downloads and infos, and here the customer projects. And if you enter here, Rhino, for example, there are some projects where the Rhino Dlubal link were used. For this project, also the Grasshopper link have been used, and for this the Rhino interface, the Baha'i Temple in Chile. You can take a short look at it. A very nice project, and you can read here Here, this line was modeled in Rhinoceros and then transferred to RFEM. Lucas, would you like to say something to the questions?
Just one or two comments regarding the questions. As I said, as I see, you mostly answered them. And there was this question if our add-on will clash with the FEM Toolbox plugin from Diego. No, it will not, because the FEM Toolbox is for RFEM 5, and this plugin that I showed you today is for RFEM 6. So it's for completely different versions. You would have to, if you want your existing structure to work with RFEM 6, you would have to use our plugin at the end of the day. And then there was a second question, instead of angle, can we use a vector to orient the beams? Yes, that's what I also showed briefly at least. You can orient them based on nodes, for example. Yes. Possible to generate the 3D wind on the elements wind tunnel according to real code in Grasshopper for a range of wind zones? No. Just basic loads, nodal line, member surface loads. Anything more advanced like the wind tunnel and so on, this needs to be done in RFEM 6 with the add-ons there. Yeah, that's, I think, all the open questions. So
yes.
I can only also say, yes, thank you for attending, at least from my side, and have a nice day.
Yeah, also from my side, thank you for your attention. Thanks to Lucas for this nice presentation. Maybe we can meet each other to another webinar. Now just take a look on our website, or if you are registered for our newsletter, you will get an email approximately 1 week before each webinar. You will get an invitation. I wish you all a nice rest of the day. Stay healthy. Bye-bye.
Bye.